Assalamualaikum. Today we're going to talk about another concept in chemistry, that is the acid-base concept. So we will try to explain, or we will try to learn what is the meaning of an acid or a base under different theories. So you know that these acids and bases, they've been important for centuries. People have been working on them, and they have been characterized, like acid has been characterized by having a sour taste and bases having bitter taste. But how they behave chemically, or what is their chemical behavior or chemical nature, that was later on explained with the help of certain theories which were presented by different scientists. So we will try to learn, or we will try to classify different molecules or ions as acids and bases in the light of these theories. So different scientists in different eras, they presented their theories about acids and bases, and as a newer theory was presented, it added more compounds into those classifications, right? So we will talk about a couple of them today. And the first scientist that worked on acid and bases was Arrhenius. So Arrhenius and Bronsted, they were the first one to work on acids and bases, and they separately tried to explain what acids and bases mean. In fact, this concept was derived when they came to know ions in aqueous solution. Later on, in 1903, he was awarded a Nobel Prize for that. And so the first theory, which explains the chemical nature of acids and bases, was the Arrhenius theory. So Arrhenius actually classified molecules into acids and bases based on the ions they produce in aqueous solution. So he defined acids as molecules which produce hydrogen ions in the aqueous solution, and he defined bases as molecules which produce hydroxyl ions in aqueous solution. So this theory was primarily, or actually it was restricted to molecules that could produce hydrogen ions and hydroxyl ions. That means that it could not accommodate other molecules which could in fact act as acids or bases, but these were restricted to molecules that produce hydrogen ions and hydroxyl ions in aqueous solution. The second limitation of Arrhenius theory was that it defined acids and bases based on the production of hydrogen ions or hydroxyl ions in the aqueous solution. So it could not classify other molecules or acid-base equilibrium or acid-base reactions in non-aqueous solvents. This theory was only restricted to molecules that could produce hydrogen ions or hydroxyl ions in aqueous solution. Second, it could not explain the acid-base nature for molecules in solid state or in gaseous state. So it is restricted to the production of hydrogen ions and hydroxyl ions in aqueous solution only. So let's say, what are the molecules that could produce hydrogen ions or hydroxyl ions in aqueous solution? So you know that there are certain molecules, when we put them in water, they dissociate into ions. So you have a molecule, a simple molecule, Ha. When you add it to water, so what happens is that it dissociates into ions. And now you can see that we have a hydrogen ion produced as a result, and we have an anion. This is a cation, and we have an anion, A-1 is produced as a result. But because we have water here as well, because Arrhenius defines acids and bases in aqueous solution, so how can you write it as H+? You can also write it as H3O plus. So this cation H plus or H3O plus is known as the hydrogen ion. It is also known as the hydronium ion or oxonium ion B is called cation. Right? So this was the general formula for an acid. For a base, if you have, for example, this molecule and you add it to water, what would happen as a result is that it will produce hydroxyl. So you have the formation of a cation, that is B plus in this case, and a hydroxyl ion is released into the water or aqueous solution. So this is how Arrhenius classified acids and bases. Now let's see some examples. So for example, we have this molecule of HCl, hydrochloric acid. If you have an aqueous solution of HCl, hydrochloric acid, what would happen as a result is that it will produce this hydrogen ion along with the formation of a chloride anion. Right, so this HCl dissociates into H plus and Cl minus. On the other hand, if we have sulfuric acid, H2SO4, if you add it to water, so it's aqueous solution, in aqueous solution it will dissociate into, again, this hydrogen ion and a bisulfate anion is produced. This bisulfate anion can then release another hydrogen ion to form sulfide anion in the second step. Similarly, you have nitric acid, HNO3. HNO3 is dissociated into hydrogen ion and nitrate anion. So these are some of the molecules or examples of molecules which produce hydrogen ions in aqueous solution, and that is why Arrhenius classified them as acids. Now let's see some examples of the bases. So a very common example of a base is that of sodium hydroxide. Sodium hydroxide in aqueous solution, or when you put this molecule in water, it dissociates into sodium ions and hydroxyl ions. So hydroxyl ions are liberated into the aqueous solution along with the cation of sodium that we have here, and that is why Arrhenius classified sodium hydroxide as a base. We can have calcium hydroxide that produces calcium ions and hydroxyl ions, so this is a base. We can have calcium hydroxide which produces hydroxyl ions when it is dissociated in water. Right? So these are some of the examples of the bases according to Arrhenius concept. Now what happens when an acid reacts with a base? We have the formation of a salt and water. So an acid reacts with a base to form salt and water. And such type of reactions are usually known as the neutralization reactions. What neutralization means is that an acid has neutralized a base, or a base has neutralized an acid. Okay, so let's see this with the help of an example, a very common example, that is HCl reacting with sodium hydroxide. So what happens as a result is that this reaction happens in aqueous solution, of course. But when you put both of these molecules in water, forming an aqueous solution, this HCl will dissociate, as we already know, into hydrogen ion and chloride ion. This sodium hydroxide will dissociate into sodium ions and hydroxyl ions. So let's see what are the ions that we have as a result. So we have H plus, we have the hydroxyl ion from here, we have the chloride ion from here, and we have the sodium ion from here. Now what happens is that this cation can attract an anion. So H plus combines with the hydroxyl ion to form water, and chloride ion combines with sodium ion to form sodium chloride, which is a salt. So in a neutralization reaction or an acid-base reaction of such types, when an acid reacts with a base, we have the formation of water and a salt is formed as a result. So the anion of the acid and the cation of the base, they combine to form a salt, depending upon the nature of these acids and bases. From nature, we mean that whether it is a strong acid or it is a strong base, or a weak acid or a weak base, you can classify these salts into different types. You can have neutral salts, you can have acidic salts, you can have basic salts. So if you have a strong acid reacting with a strong base, then the salt that is formed usually is a neutral salt. If you have a strong acid reacting with a weak base, then usually it's not a neutral salt. It may be an acidic salt, or in other cases, it may be a basic salt as well. Right? So we're not going into that detail or the strength of an acid and base, that we will discuss later on. But here, this is just to tell you that in a neutralization reaction, an acid and base react to form salt and water. So you can apply this concept to different molecules that can produce hydrogen ions and hydroxyl ions only. And so it is limited to molecules that produce such type of ions. Plus, as I told you earlier, it is limited to reactions in aqueous solution. So nothing can be explained in solid phase or in gaseous phase. And third, molecules that do not produce these ions, the hydrogen ions or hydroxyl ions, that could not be classified into acids and bases according to Arrhenius concept. So later on, another concept was introduced, and that added more molecules into the table of acids and bases. So let's see the second concept. So the second is the Bronsted-Lowry concept. These are two different scientists, and they separately developed this concept or presented this theory of acids and bases, and then it was combinedly known as the Bronsted-Lowry concept of acids and bases. According to the definition of Bronsted-Lowry, acids are molecules, or they may be ions, that can give or they can donate hydrogen ions to other molecules or ions. And bases are molecules or ions that can attract, or they can abstract, or they can accept hydrogen ions from other molecules. Other molecules mean from acids. And again, bases could be neutral, or they can be in ionic form as well. So according to these concepts, acids are hydrogen donor, hydrogen ion donor, and bases are hydrogen ions acceptor. In the previous concept, we were talking about the production or the liberation of hydrogen ions and hydroxyl ions for acids and bases. But here, we are actually talking about give and take. So acids give hydrogen ions, and bases accept that hydrogen ions. So it's a mutual reaction between acid and base. इसका मतलब ये है कि आप एक मॉलिक्यूल को एसिड या बेस तब कह सकते हैं जब उसके साथ कोई दूसरा मॉलिक्यूल मौजूद हो और वो इसको हाइड्रोजन आयन या तो प्रोवाइड करे या इससे एक्सट्रैक्ट करे। तो अगर दूसरा मॉलिक्यूल इसको हाइड्रोजन आयन प्रोवाइड कर रहा है तो वो एसिड होगा, ये खुद बेस होगा, या अगर इससे हाइड्रोजन आयन ले रहा है तो फिर ये एसिड है क्योंकि ये दे रहा है, और जो इससे ले रहा है वो बेस होगा। Right, so it's a mutual reaction between an acid and a base. Right, so इसको आप simply इस तरह से लिख सकते हैं. For example, we have this molecule HA, and we have another molecule that is B. We don't know which one of these is an acid and base, but when they react together, what we get as a result is an anion A minus plus HP with a positive charge cation. You see the charges on left and right hand side, they should be equal. So this is neutral, both are neutral. Here we have the formation of ions. Now this HA has provided, or it has given away a hydrogen ion, and that is why now it can be seen as an anion. लेकिन ये H ion इसने किसको दिया? This hydrogen ion has been donated to B, and this B here has accepted this hydrogen ion, and now you can see it in the form of a cation, right? So we have the formation of an anion here and a cation. So now you know that this is an acid because it has given away the hydrogen ion, and anything, according to Bronsted-Lowry concept, if it provides or it gives or donates hydrogen ions, is an acid, and anything that accepts this hydrogen ion is a base. Now, with this, another concept was introduced. As I told you earlier, that according to this concept, the Bronsted-Lowry concept, we can classify molecules or ions as acids and bases depending upon their mutual reaction. So now from this general reaction, you can clearly see that this is an acid and this is a base. So with this, another concept was introduced, and that was the concept of conjugate acid and base. So what does that mean? So any acid that gives away a hydrogen ion, and here in this case, in this general reaction, it is converted into an anion here. So you can say that this anion or A minus is the conjugate base of this acid. And this base, after abstraction of proton or acceptance of a proton, is being converted into this cation. So this is the conjugate acid of this base. Now why we call them as base and acid? You can clearly see from the chemical nature of these two species. Here we have an anion, A minus 1, and here we have a cation, B, with a hydrogen ion having a positive charge. So, you already know that ions, they are highly unstable. Ions are highly unstable, and that is why they are highly reactive. So, anything that could get rid of this charge for these species, these ionic species, would be welcome, or any change or any reaction. So this minus charge can be neutralized by anything that is positively charged. अगर आपके पास -1 charge है, इसको 0 मिलाने के लिए, you have to provide it with a +1 charge. So to neutralize this -1 charge, you need any species that has a +1 charge. So this A minus will undergo a chemical reaction with anything that is positively charged to neutralize itself. And here we have a cation. We have a +1 charge on this pH. So anything that could help this pH ion get rid of the +1 charge would be welcome. So it can, from its chemical nature, we can say that it can liberate or it can get rid of a hydrogen ion, and hydrogen ion will leave with a +1 charge. leaving behind this B as a neutral solution. So it can happily liberate or it can donate a hydrogen ion. And according to this concept, you know that anything that can donate a hydrogen ion is an acid. That's why we call this an acid. And this anion would accept a hydrogen ion to neutralize its negative charge. So anything that can accept a hydrogen ion would be a base. So what can happen as a result is this anion can extract this hydrogen ion from Hb plus to form Ha back, and B will be left neutral again. So you can also have a reverse reaction. So the concept of conjugate acid and base was introduced along with the classification of molecules or ions according to into acids and bases according to Bronsted-Lowry concept. Now, what are the relative strengths of these acids and bases or conjugate acids and bases? For example, we have a strong acid here and we have a strong base here. So any strong acid reacting with a strong base would give rise to these conjugate acids and bases. If the acid is strong, generally we say if the acid is strong, the conjugate base would be weak, and if the base is strong, the conjugate acid would be weak. On the other hand, if we have a weak acid, its conjugate base would be strong, and if we have a weak base, its conjugate acid would be strong. So, according to this concept, acid is anything that can liberate hydrogen ions or it can donate hydrogen ions. So, any species that can happily donate hydrogen ions is an acid. So, if we have a stronger acid here, it would happily donate a hydrogen ion to form this anion, which means, on the other hand, that the anion that is produced as a result would be relatively more stable. Although ions are unstable, we are talking about relative stabilities. They are unstable, they have to react. But we can have different anions. Some would be more reactive, others would be less reactive, or we can say some would be more stable, others would be less stable, depending upon their makeup, depending upon their atomic size or the ionic size or charge density. So if we have a strong acid, it will happily donate a hydrogen ion to form this conjugate base A minus. Now this conjugate base or the anion that is produced is relatively stable. In other words, you can say that it might have a lower charge density. So it can accommodate this negative charge to some extent. And that is why it would not be very highly reactive. So it could stay for some time in this anion form. And if it can stay in this form, then we say that it's not much reactive. If it is not much reactive, we say that it's a weaker base. The capacity of this base to abstract a proton is slightly lower because of its more stability or less reactivity, right? On the other hand, if we have a weak acid, its conjugate base will be strong. So a weak acid means that any acid that is reluctant to donate a hydrogen ion. It will donate a hydrogen ion, but reluctantly. So it dissociates into hydrogen ion and an anion here, but it's not happy because it's a weak acid. So the anion that is produced as a result would automatically be highly reactive. And that is the reason why this HA is a weak acid, because its conjugate base is very strong, it's highly reactive, its charge density is higher, its charge is not stabilized, or its charge is not dispersed over a larger area. It is accumulated on one atom or a certain part of this anion. So this is highly reactive, highly unstable, and it will quickly abstract a proton from anywhere from any molecule that can provide it. So if it is highly reactive or it can accept proton abruptly, that means it's a strong base. So weak acid will produce a strong conjugate base. Similarly, if we have a strong base, so strong base has the capability of extracting a proton much more than a weak acid. So if it can accept a proton happily or a hydrogen ion happily, it will be reluctant to leave it back. It will produce a cation here, which is unstable, but this cation would not be as reactive as some other cation or anion that is produced in some other reaction, but it will be relatively more stable as compared to others because this base is happy to accept a proton. So if it is happy to accept it, it will be reluctant to give it back. It will give it back because it's an ion, and you know that this acid has a property of donating a proton or a hydrogen ion, but it will be reluctant to give it back. So if it is reluctant, it will stay here for some time. That is why we say it's a weak acid. On the other hand, if we have a weak base that is reluctant to accept proton, then it will accept a proton, but it will not be happy to keep it for a long time. So it will quickly give it back. So if it quickly donates a proton, that means it's a strong acid. So with Bronsted-Lowry acids and bases, we have another concept of conjugate acids and bases. So let's see this with the help of some examples. But before that, let me repeat it again that in Arrhenius concept, the classification was only limited to the production of hydrogen ions and hydroxyl ions. And here you saw that we don't have any hydroxyl ions. In fact, it is the donation and acceptance of hydrogen ion or H plus between two different species, and that is when we can classify them as acids or bases. Second, Arrhenius concept was limited to acids and bases in aqueous solutions only, but here we can have examples in which acid-base reaction can occur in non-aqueous medium as well. For example, in liquid ammonia, you can have different types of reactions in which we can classify molecules as acids and bases. A common example that you might or might not have seen is that of this ammonium chloride. If we have ammonium chloride here, and for example, we have an amide. This is known as an amide ion. Let me write it in the form of molecules. Sodium, right? So we have ammonium chloride and sodium, and this reaction, it occurs in, or it happens in liquid ammonia. Liquid ammonia is a solvent, and reactions can take place in liquid ammonia. So what will happen? See, this ammonium chloride will dissociate into ammonium ions and chloride ions. This sodiumide will dissociate into sodium ions and amide ion, NH2 minus 1. Let me first write the dissociation reactions, and then we will talk about the acid-base reaction. So ammonium chloride is dissociated into ammonium ion and the chloride ion. Sodium ion is dissociated into sodium ions and amide. So you know that we have these four different ions, two cations and two anions. And now you can see here that this chloride ion and sodium ions, they will react together to form sodium chloride, which is the formation of a salt. But what about these two species? This is a simple anion and cation reaction, forming sodium chloride. But what about this ammonium ion and this amide ion? So let's see the reaction between ammonium ion and amide. So now we have ionic species. We have a cation here and we have an anion here. And as I told you earlier, ions are highly unstable, so they will try to get rid of the charge. This ammonium ion will try to get rid of the positive charge. This amide ion will try to get rid of the this negative charge. So what can happen to get rid of these positive and negative charges is that this ammonium ion can liberate, or it can donate, or it can give away a hydrogen ion. So when a hydrogen leaves in the form of hydrogen ion H+, it will take away the positive charge with it, leaving behind NH3. And NH3, you know, is a neutral molecule, ammonia. But this hydrogen ion, it is donated by the ammonium ion, so it will be extracted by this amide ion. Because all of these are present in the same solution, so this amide ion, again, where the negative charge is highly unstable, so it would be happy to extract this H+. So H+ from this ammonium ion is donated to this amide ion. So what would be the result of after extraction of hydrogen ion by amide? This will take up a positive charge, neutralize its negative charge, and that positive charge is coming in the form of H. This would be converted into NH3. So we will have the formation of two ammonia molecules. One after the donation of hydrogen ion by ammonium ion, and one after the formation of after the extraction of hydrogen ion by the amide ion. Let me write it in this form. Let me write it in this form. NH3 plus NH3. Now, ammonium ion has donated a hydrogen ion. So anything that donates a hydrogen ion will be an acid, and this amide ion has abstracted, or it has accepted a hydrogen ion. So anything that accepts a hydrogen ion is a base. Now, this ammonium ion, after donation of the hydrogen ion, is left as NH3, or it is converted into NH3. So this ammonia that is produced after donation of hydrogen ion by ammonium ion is the conjugate base of the ammonium ion. And this amide ion, after acceptance of hydrogen, is converted into ammonia. So this ammonia is the conjugate acid of this amide ion. Right? So you can see now here we have an acid and a base, an acid-base reaction, giving rise to the conjugate acids and bases. And interestingly, in this case, both the conjugate acids and bases are the same species. Now, what are the strengths? You see ammonium ion here, it's an ion again. So when you compare it with a neutral molecule, it is highly reactive. Comparing with a neutral molecule, this ion is more reactive. So it will happily donate a proton. So it's a strong acid. Its conjugate base is weak. This is a conjugate base. See, ammonia. Why? It's a weak conjugate base. Base, according to this concept, is anything that accepts a proton. This ammonia would not be much happy to accept a proton from this second ammonia, because that will convert this neutral molecule into an ammonium ion. It may accept, but in other conditions, when you have a stronger acid, in this case, it will not be happy to accept a proton. That is why it is a weak conjugate base. Amide ion is an ion, and it's highly unstable. It will be happy to accept a proton. So it's a strong base, and that is why its conjugate acid will be weak. But this conjugate acid, ammonia, will not be very happy to donate a proton, because that will then convert it into an ion. So going from a neutral molecule to an ion, that is not very feasible. That is why it's a weak acid. It's a weak base. These are strong acids and bases. So this is how you can classify molecules into acids and bases according to Bronsted-Lowry concept. You can apply the same concept to other acids, Arrhenius acids as well, like for example HCl. HCl is an acid in both cases. Sulfuric acid is an acid in both cases. Phosphoric acid, nitric acid, you can classify them as acids in both the concepts, right? So we will talk about some other concepts in upcoming lectures and with the help of some examples. Thank you so much for now.